Hello and welcome to another Decision Maths video. This time we're tackling question 1 of the June 2023 Edexcel Decision 1 paper. And we've got figure 1 showing this graph here. And we're asked to state whether G is Eulerian, semi-Eulerian, or neither, giving a reason for our answer. So it's important to consider that a graph is Eulerian if it has no odd degree vertices or no odd vertices. It's semi-Eulerian if there's exactly two odd vertices, and otherwise it's neither. So let's see how many odd vertices this graph has. A has degree 3, B has degree 4, C has degree 3, D has degree 3, and E has degree 3. So the answer to this is going to be neither. As there are more than two vertices with an odd degree. Okay, we're asked to write down an example of a Hamiltonian cycle on our graph. So a Hamiltonian cycle is a cycle or a path that goes through every vertex exactly once and back to the starting vertex. So one example that I have is going to be A, B, C, D, E, A. We're starting at A, I'm going to use a green pen for this. Starting at A, going to B, then to C, then to D, then to E, and back to A. Okay, question C, we're asked to state whether or not graph G is planar, and we need to justify our answer. So you might be really tempted to use a planarity algorithm for this, and it would work. We've got a Hamiltonian cycle, so we can use a planarity algorithm, but we could conclude that G is planar as it can be drawn with no arcs intersecting. As long as we can accurately conclude that, that would be accepted as a reason. But in order for us to accurately conclude that, we'd actually have to show it being drawn with no arcs intersecting. And we can do that. If instead we didn't have AC cutting directly through the graph, but instead had AC going all the way around, we now no longer have any edges crossing. So it's planar. Okay, next up, we're asked to state a number of arcs that would need to be added to G to make a graph K5. So it's actually really important. There's two different methods. You can either consider the number of edges that K5 has and the number of edges our graph has and find the difference. Or you can try adding edges to our graph as it is. So I'm going to delete my scribblings on the graph and I'm going to add edges until I can't add any more. So B is already really well connected. So it's only these other vertices I need to consider. So let's try connecting A and D because A and D aren't connected. A and D will now have a degree of 4. And so are connected to all 4 other vertices. So the only other edge we need to add in is CE. And if we add that in, C and E will get degree 4. So all the vertices have degree 4 and we have a K5. How many edges do we add in? 2. Last but not least, we need to set up an initial time matrix for Floyd's algorithm and perform a final iteration of Floyd's algorithm. So let's try this now. So setting up our initial time matrix, we are only considering direct connections between vertices. So we aren't considering routes that we can spot. We can only consider the edges that we have, like a computer would. So AB is 10, and so is BA. And actually, a really good skill is to be able to identify that this isn't a directed graph. So our initial time matrix should be symmetrical down the leading diagonal. So we actually only have to fill in half of it and then reflect it. A to C has length 15. A and D are not connected, so I'm going to write infinity. And finally, A and E have distance 5. Next up, B to C has distance 3. B to D has distance 8. And B to E has distance 4. C to D has distance 2. C to E doesn't exist, so it's going to get infinity. Finally, D to E has distance 7. So now we can just reflect what we've already got. Excellent. So now we're told, and we're given the time matrix after 4 iterations of Floyd's algorithm. And we're asked to perform a final iteration. So I'm actually going to shade in my final row and column, just so I know what values are staying the same. And now that I know these values are staying the same, I can copy them directly. And now I need to consider whether any of these values are going to be reduced. So A to B currently has time 10. If I do A to E with time 5 and E to B with time 4, this is going to improve to have time 9. A to C is 13, but A to E and then E to C has time 5 plus 7, which is 12, and 12 is better than 13. A to D, I can add up the 7 and the 5 in the column and row next to D, and 7 plus 5 is 12, and 12 is better than 15. Next up, 3 is smaller than 7, and it's smaller than 4. I know I'm not going to make an improvement. 5 is smaller than 7. I'm not going to make an improvement. Finally, 2 is definitely smaller than 7 and 7. So I'm not going to make an improvement. And because my graph is an undirected graph, I can reflect this. So I'm going to get 9, 12, 12, 3, 5, and 2. And that's a final iteration. So you're going to get a B1 for correctly setting up the initial time matrix. You're going to get an M1 for reducing 2 values correctly. There are only 3 values that needed to be reduced, or 6 if you include the column. So as long as you reduce 2 of them correctly, you'll get the method mark. And you'll get the final accuracy mark for doing the entire process correctly. So thanks for watching, and until next time, goodbye.